Hi, I'm Kent Whitfield, VP of Quality at Nextracker, and I'll be talking today about the hail impact test and potentially moving beyond 25 millimeter hailstone diameters. I'm joined in this presentation by Cherif Kadir, who's the CEO of the Renewable Energy Test Center. I'll be providing a little bit of background on the test, and then Cherif will tell us a little bit about some of the data that's being gathered as part of an extensive DOE. So whenever we talk about a PV research topic, we inevitably will end up with a report from the Jet Propulsion Lab issued in the decade between the mid-70s and mid-80s. The volume of work that this group did is really nothing short of remarkable. And with regard to hail impact, we could look at this final report that was issued in October 1986, for which a statement is in the report saying that the final Block 5 test picked 1 inch because it would achieve acceptably low probabilities of failure, even in low hail incidence regions of the country. Okay, makes sense. Now, the report also kind of covers susceptibility of failure and shows that, something in the 1 1/4 to 1 1/2 inch hailstone size would be sufficient to cause tempered glass to break. And so we really need to answer some questions here. Has something about the environment changed? Has location of where we're putting projects today changed? Or have anything about the module susceptibility to failure changed that would force us to want to reconsider this particular test? Now, it's always good to ask the question, what is it that we're worried about? And certainly we're worried about hail. Hail can come from different sources. Generally speaking, the marine or orographic sources of hail tend to be fixed in geographical location and small in hailstone diameter. Typically, what we're worried about is this macro scale synoptic, which is associated with weather fronts that's producing swaths or streaks of hail that can be fairly large in size. And much more practically speaking, what we're worried about is damage like shown in the picture here, which is from a large system that was located in Texas in 2019. Now, broken modules are easy to see and easy to replace. The other thing that we need to be worried about is cell damage, where the glass isn't broken, but the cell's damaged and the performance is impacted accordingly. This is much tougher to find in the field, so it's more expensive to locate and replace. Now, most of what we know about hail comes from NOAA's Storm Prediction Center's severe weather database. This is arguably the largest data set in the world covering severe weather occurrences. And the source of this data are personal accounts. These personal accounts may come from app submissions, internet form submissions, or even phone calls. Actual weather station reports represent less than 2% of the data in this database. And this means that there are some non-trivial uncertainties associated with it, including a bias for larger hailstone sizes than what actually may occur in particular sites. Nevertheless, it's the data that we have available, and it's available in geographic precision that's actually pretty respectable. If you haven't gone to the Storm Prediction Center, I'd encourage you to do so. You can find a number of figures and animations, such as the one I'm showing here, which shows the probability of a 2-inch or larger hail impact over the course of a typical year. And we see that the probability starts out in the Texas, Oklahoma area, goes up to a maximum of about 1.2%, and then kind of travels northward, okay? Now, if we compare that with data, one of the most thorough data analyses from the late 1970s, the JPL, they said for the Great Plains region, you could expect a 1.5 inch or larger hailstone impact every 6 to 8 years. Wow, okay. Yeah, if we take the data available in the severe weather database and we fit it to a Gumbel extreme value distribution, we can come up with a 5-year recurrence interval figure, such as the one that's shown in the lower right-hand side of this slide. For what you see in the regions in blue, you can expect something in the 1 to 2 inch or larger range, and in the green in the 2 to 3 inch or larger range every 5 years. Wow, okay. So really what this says is that the environmental exposure really hasn't changed significantly in the last 40 years. And in fact, most research would say that the frequency or number of hail days by location really hasn't changed. And although we see the observances of hail increase, it tends to be in areas where there are growing population centers. So it's basically a confound, and it means maybe we're just getting more effective at seeing what's already there. Now, on the other hand, if you have a hail event, higher levels of convective atmospheric potential energy that are brought about by rising surface temperatures could lead to larger hailstone sizes. Okay, but it's these last 2 points that I think are maybe the most important. One is that the size of PV systems has gotten extremely large, as would be indicated by this photo on this slide. Secondly, PV systems are now being sited because of economics in locations where it didn't used to make sense. So we are seeing now more systems going into the Texas and Oklahoma area. So this means that, ultimately, we've got to acknowledge reality, and that is that we are going to see more systems going in east of the Rocky Mountains, meaning that they are going to be subjected to hail events larger than 25 millimeters within reasonably short recurrence intervals. Therefore, we should understand the risk of damage in especially the 2 to 3 inch hailstone range, or the 50 to 75 millimeter. And then ask ourselves, are there things that we can do to reduce risk, including active strategies, which is something that Nextracker we've been very interested in, or in the materials used to make modules and the manufacturing methods. Now, to speak more on some of these, I'm going to now turn it over to Cherif to walk us through some of the data that's been gathered. Cherif?
Thank you, Kent. Hi, everybody. Thank you for tuning into this talk. As Kent mentioned, these hailstorms are a fixed event. I mean, they will happen and they will continue to happen. Now, what we need to understand, what we set out to understand, is how modules will behave under these hailstorm conditions, and whether the certification standards that module manufacturers abide by are sufficient to assess the risk associated with these modules as they're installed in hail-prone areas. So a quick look at some of these standards. We looked at IEC, obviously, 61215 and 61730, which are the dominant standards. But we also looked at FM Global. We looked at ASTM 1038, as well as some industry research on hail storms and energy impact associated with hailstones. And so if you look at IEC 61215, for instance, it provides a table in there that covers 25 millimeters all the way up to 75 millimeters hailstones in diameters. And it provides their associated expected masses and test velocities. If you look at FM Global, it provides maybe a little bit more color in terms of types of hail impact based on expected severities, and I'm assuming of installations. And then if you look at ASTM, it provides a little bit more detail. The coverage is from 15 millimeters all the way to 85 millimeters hailstone diameters, and their associated masses, and the mass is provided as a calculation based on the ice density. But when it comes to test velocity, they provide a calculation to modify the test velocity based on expected wind speeds. And those wind speeds range from 0 miles per hour all the way to 30 miles per hour. Now, if you look at, for instance, the 0 miles per hour, it tends to line up pretty well with the IEC standard. And I'll go more into that in the next slide. Now, ASTM provides more color in terms of how the tests can be performed. They can be prescribed. For instance, if modules are put in a position in the field, say in the stowing position that allows for the back of the module to be subjected to hail impact, then the back of the modules should be tested. And so we looked at that in some of our testing. So the paper that I mentioned and some of the literature that we mentioned had one interesting fact, and that is in this particular paper by Fluler et al., he noted that in his research, or in their research, they found that there was a variety of papers out there that stated a wide range of terminal velocities associated with different hailstone diameters. What we determined is that it kind of could be explained by the ASTM standard. The ASTM standard, if you adjust for the wind speed during a hailstorm, you will see that they basically determine that the terminal velocity of the hailstone should be modified and potentially increased. What doesn't compare very well with the paper and the research out there is that ASTM's calculation shows a diminishing impact of the wind speeds on the terminal velocity as the hailstone diameter increases. And that could be observational on the paper side. But one thing that's interesting is in the Fluler paper, he picked a set of constant variables, which essentially made his assumptions to be the median or the mean of all the observations in the papers that he looked at. And now if we take that and overlay Fluler's assumptions on the hail velocities prescribed by IEC and the ASTM with the assumption that wind speed is equal to 0, they all line up almost perfectly. And so the only determining factor there is the hailstone diameter. And so, of course, in the industry, what's predominantly used is this particular point here, 25 millimeters is what determines whether you get an IEC certificate or not. And so we went ahead and tried to understand how these modules are going to behave in real life conditions when hailstones are not 25 millimeters and are a lot greater. And we try to assess the impact on a variety of different modules. And so in our design of experiments, we tried to cover a variety of different manufacturers, a variety of different hailstones. And so since all the standards seem to agree, including the research that we looked at, we just opted to follow IEC 61215 guidelines, where it specifies hailstone diameters ranging from 25 to 75 millimeters, and it specifies the mass and test velocity, so it was very easy to follow. And for any non-prescribed hail diameters, we essentially just used linear regression to project the test velocity, which was a very easy thing to do. And then as far as the ice as far as the mass of the hailstone, we just used the ice density calculation to verify the hailstone mass, and that was really not an issue at all. So if we have say a 60 millimeter hailstone, we could predict its mass mathematically, and we could verify it by weighing it. So again, we looked at different manufacturers, and for those manufacturers, they had different bill of materials, different glass constructions, different glass thicknesses, obviously, different EVAs, backsheet versus glass substrate, as well as different cells and junction box locations. So, we tried to cover quite a bit of different variables, and the DOA is still ongoing, but we're reporting some of the results in this. So one of the interesting and notable points here to make is that the 3.2 millimeter glass constructions used glass that was tempered. 3.2 millimeter tend to be tempered. The 2.0 millimeter glass tended not to be tempered. And from what I understand and our discussions with manufacturers, that glass tended to be heat strengthened. So it's not just simple glass. It goes through a strengthening process. It's just not as tough as the 3.2 millimeter glass. And you can notice this in our test results in the break pattern. Again, we use different hail sizes, impact energies. We also looked at different impact angles. And we're also looking at different temperatures of modules, which is going to be published shortly after this conference. Now, as far as the results, looking at the 2 millimeter modules, which predominantly were bifacial modules, we've seen from historical constructions of modules submitted to us in 2019, failures starting at 45 millimeters, and those broke whether they were impacted from the front or the back. Again, this is referencing the ASTM standard in case the module is put in a position where it could be impacted from the back. The new constructions, modules we received later in the year of 2020, somewhere around Q3, Q4, we noted that they started breaking around when impacted with 55 millimeters hailstone. And again, they broke whether we impacted them from the front or the back. And of course, in all our testing, we increased the impact energy. So we would start with 45 and then 50 and then 55 until we start seeing a consistent break. On the 3.2 millimeter front glass with polymeric backsheet, again, test conditions at 25 degree ambient temperature, direct impact yielded breaks at about 75 millimeter hailstone diameter. And again, we impacted the modules from the back with 75 millimeter hailstone, and the front glass broke just the way it did when we impacted it from the front. And one thing to note, of course, is we didn't just start at 75. We went slowly into, we increased the hailstone diameter until we started seeing a break. And in this case, at 65 millimeter hailstone, for instance, the module did not break. However, it did cause cell cracks. So some visual representation of the failures that we saw. These are the 2.0 front glass and back glass, which did not break at 50 millimeter hailstone impact, and they broke at 55 millimeter hailstone impact. The images on the left show a front side impact, and you could see that even in the break pattern, it's not very typical of tempered glass. And then when we impacted the module from the back, you can see the break as well. And so, one thing to note here is whether we impacted the module from the front or the back, both front and back glass broke. The break did not stop at just the glass that was actually impacted. On the 3.2 millimeter construction with 3.2 millimeter front glass and polymeric backsheet, these are the images of the breaks. And so when the module was impacted on the front side, it broke, and you could see the break pattern. You could see the typical shattered glass, and it propagates all throughout the module. And then in the middle image, it shows you the impact from the back and its result on the front glass as it shattered. And so what we did is to test the theory that, well, if the modules were to be positioned in such a way that the front glass is not facing the hailstones, that could potentially save the modules from breaking. Well, potentially, yes, maybe, but our testing shows that it's not the case for us. And if the impact energy that causes the front side to break will also cause the front side to break if the impact comes from the back. However, in the event that a module is impacted on the backside, on the polymeric backsheet, it's going to cause severe cell damage. And in this case, the front glass did not break with the 65 millimeter hailstone, but it caused, the impact caused severe damage to the cell. So what we did is we dropped the impact severity. So we went and maybe Zen, please cut this part. So what we did is, and here I'd like to show you a video of of the actual test showing 3.2 millimeter glass being impacted by 65 millimeter hailstone, and then being impacted by a 75 millimeter hailstone. And you could see the differences in the glass being completely shattered by the 75 millimeter hailstone versus the 65 millimeter hailstone. Now, one thing we did is we dropped the hailstone size to 45 millimeters, which is a 5x reduction in impact energy. And we impacted the 3.2 millimeter module, not the same, different module, but same construction, from the back, just to see, okay, in an event that an O&M or developer decides to say, try to save the glass by turning the modules away so that they're impacted from the back. And this is based on some information, some publications we saw in the industry that that could be a strategy to save the glass from being damaged. What we found is even impacting the modules with 45 millimeter hailstones, which would usually not cause any damage or any substantial damage to modules on the front side, will definitely cause a lot of cell damage because the cells are no longer protected by the thick glass on the front, and the impact on the polymeric backsheet will cause all of that energy to be transferred directly to the cells. Now, one slide that Kent showed was really interesting, and it shows that in hailstorms, whenever, and I'm sure a lot of people saw this, you see a lot of modules that are damaged, the glass is completely shattered, but then you see some modules within the same strings that survive. And one fear is that developers may replace the modules that are visibly damaged and leave the modules that are not broken in the field. And this is what happens. So what we did is we took a module that did not break. Sometimes modules don't break at 75 millimeter hail impact. So we took a module, impacted it at 75 millimeters and with 75 millimeter hailstone, and it did not break, which is great news. But then this is what happened to that module. This is what happened to the cell. And this just essentially highlights the risk associated with these modules beyond the glass, beyond the break that is visible by the O&M team when they go out there after a hailstorm and decide to replace modules that are broken, and maybe potentially not replace modules that are not that do not show glass breakage. So, of course, there are some mitigation strategies out there, and what we did in our DOE is we tilted the modules, and what we found was tilting modules made with 2.0 millimeters and 3.2 millimeter front glass yielded different results. The 2.0 millimeter glass required at least a 30-degree tilt before they could pass the impact that caused them to break when impacted directly. And so, at 15-degree tilt, for instance, the modules broke with 55 millimeter hailstone. With the 3.2 millimeter glass, a 15-degree tilt allowed them to pass the 75 millimeter hailstone impact, which was great. Of course, the disclaimer here is not all modules are the same, and of course, this, different constructions, different tempering processes, heat strengthening processes, different bill of materials, and we're collecting more data from different manufacturers and different bill of materials to be able to have a more holistic view of how these modules are going to behave. Now, what are the next steps? Obviously, the key takeaway is different manufacturers with different modules are going to react slightly differently to these events. But in general, we do see clear trends that thinner modules with thinner glass are going to break at lower impact than previously deployed modules with thicker front glass. What is urgent right now, I think, in the industry is to pull together a task force to fully understand the risks associated with hail, especially as modules are being deployed in more hail-prone regions, and as the modules deployed utilize glass that is thinner and potentially less durable than 3.2 millimeter conventional modules. And I think it's also really important for the IEC standard to reevaluate the requirements and not simply provide a table that states, as long as you pass any of these conditions, you're going to be issued a certificate. A module that is going to be deployed in California, for instance, can be tested to 25 millimeter hail impact, and that will probably be okay. But that module is probably not going to be okay in a region where it's likely going to see 2 or 3 inch hail impact. And so the IEC committee and the standards must take that into account and must come up with better guidance for module manufacturers to better comply with maybe ways to better rate their modules for different hail-prone regions. Thank you for coming to this talk, and I'd like to give a shout out to the team that contributed to this great work. Thank you very much.